Hello, everybody. Welcome back to part 3 of this lecture, chapter 4, time response. So now we would like to talk about underdamped response. So one more time, the underdamped response, we should expect that we will have two complex conjugate poles. So the poles will consist of one real part and imaginary part. How can we do this? So we need first to get the characteristic polynomial s squared plus 2s plus 9 equals 0. Find the poles. We will use the law. One more time the law. If you have an equation such as if you have something like ax squared plus bx plus c equals 0, so your roots will be x1, 2 equal minus p plus minus square root b squared minus 4ac divided by 2a. So now we can do it. So if we need to apply this one to the characteristic polynomial, so minus b here equal 2, so it will be minus 2 plus minus square root b squared, it will be 4 minus 4ac, 4 times a times c, 4 times 9, it will be 36, divided by 2a, which is 2 times 1 is e. So minus 2 divided by 2, it will be minus 1 plus minus square root 4 minus 36, it will be 32. So 32 is 4 times 8. 4, it will go out from the square root of 4, it will be 2. 2 divided by 2, it will be 1 here. The coefficient here, it will be 1. And what will remain will be square root of minus 8. Square root of minus 8 is plus minus j multiplied by square root of a. If you want to make it more simple, you can write this one as 2 square root of 2. So we can say that, okay, this one will be minus 1 plus minus j multiplied by 2 square root of 2. It will be like this one. So, so we have those two complex conjugate poles. So we will have one here and one here. This is the real part, which is minus 1. And we have the imaginary part, which is j plus j square root of 8 and minus j square root of 8. If you want to get omega n, or natural frequency, damped natural frequency, it will be this distance. So this one, in fact, it will be square root of that part plus a square root of that part. So it will be square root of, if I need to get omega naught, so it will be square root of minus 1 square plus square root of square root of 8. So in fact, it will be square root of 1 plus 8 will be 9, so it will be 3. So we can say that the damping frequency, it will be 3 radian per second, right? If you want to get minus eta, if we need to get eta, for example, so it will be minus eta omega naught equal minus 1. So zeta will be 1 divided by omega naught. So it will be 1 divided by 3. So it will be 0.33, which is less than 1, correct? It's less than 1 because this system is underdamped, right? So if we can go back here to this table. So this is the response of underdamped system. And you can see that zeta is greater than or equal 0 and less than or equal 1. And for our system, it will be 1 divided by 3, which is this one. So here, zeta, it's greater than 0 and less than 1. For this system here, zeta equal 0.3. So we have this damping. And therefore, we can see that we have this damping effect. So we got this solution, we solved it, and we got the real part equal minus 1, the imaginary part equal that part. If you want to get zeta, as I told you, yes, we got it already. So this one will be, if you want to get zeta, so it would be, yeah. So this one negative, in fact, minus zeta. So it's minus zeta omega n equal minus 1. So zeta will be 1 divided by omega n equal 1 divided by 3. If you want to get omega 0, so omega 0, we will get it from this pole 0 plot, right? Those pole 0 plot. This one, this distance equal to omega n or omega 0. So omega n will be square root of the real part, which is minus 1 square plus square root of the imaginary part, which is that part, right? which is square root of 8, right? So it will be square root of 9, which equal 3. So now we have the natural frequency and we have the damping ratio. We have the natural frequency and we have the damping ratio of your system. So if you want to get the solution, by inverse Laplace transform, so we know, I mean, this is a block diagram. So the input of your system is R of S, the output is C of S. We have here the transfer function G of S. So C of S equal G of S multiplied by R of S. C of S equal G of S multiplied by R of S. For step input, R of S will be 1 divided by S. So the total C of S will be 9 divided by that part, right? This is complex conjugate pools, so it will be 9 divided by S multiplied by S plus 1 plus this one. In fact, we need to just J, right? This one also will be J, correct? So I need to find the K1 and the K2. So now we have K1 divided by that part. We will use partial fraction expansion. So we have a complex fraction will be composed into a summation of simpler fractions. So it will be K1 divided by S plus K2 divided by this one plus K3 divided by that part. You will solve it and you will get the value of K1, K2, and K3. And finally, you will solve your equation and you will get finally this one. So C of T will be this one. So you just need to go to the Laplace transform table and try to find something. In fact, you don't need, in fact, to factorize this one. I guess factorizing it is not correct because yeah, but it will be A multiplied by exponential real part multiplied by D cosine omega dt minus phi. Phi is this angle. So this is phi, right? This is phi, right? So in fact, if you need to get this one, you can get it by tan. It's arc sine zeta, right? Or it could be tan minus 1 that part divided by the real part divided by the imaginary part. Yes. So the poles are complex. I mean, for this underdamped response, the poles are complex conjugate. So those will be the poles minus eta multiplied by omega 0 plus minus j square root 1 minus zeta square omega 0. Remember, for our example, zeta equal 1 divided by 3 and omega 0 equal 3 rate per second, right? The less zeta, the less damping in the step response. It can be shown that the less zeta, the more dominating imaginary part over the real part of the poles. This is a general property of poles. The larger imaginary part relative to the real part, the less damping in the time response. Yeah, I mean, we will have this figure here, you see? Or one more time, I mean, this is the damping ratio. I mean, we know that this is complex conjugate poles. This is the real part, which is equal to zeta multiplied by omega n. And we have here the imaginary part, which is square root 1 minus zeta square multiplied by omega n. So when zeta is smaller, you will be closer. I mean, the damping ratio will be less. I mean, when you decrease zeta, what will happen? Imagine zeta is 0.9 and maybe 0.1. From when it's open 0.1, you will be closer to the g omega axis, correct? And then when it's larger, you will be far away from this one. When you are closer, what will happen? Damping will be less, correct? And then when damping is less, it will be 0. When it's 0, in fact, we will have this case. Our system will be undamped. So when the damping ratio is high, you will be far away from the g omega axis. When it decreases, what will happen? You will become closer to the g omega axis. And then when you are closer to the g omega axis, what will happen? The damping effect will decrease until it becomes 0. And then when it's 0, in fact, your poles will be just imaginary. So it will be this case. It will be undamped system, because for this undamped system, eta or zeta equal 0, right? So your system will just keep oscillating. There is no damping effect. As you can see here, it's oscillating. So you will keep this oscillation all time. It will not damp it, right? It will not decrease. You will keep this oscillation with time because the damping effect equal 0. So just imagine that when zeta equals 0, your complex conjugate poles will be located at the g-omega axis. The real part will be 0 because this real part equal eta or zeta multiplied by omega 0. So when zeta equals 0, it means the real part will be 0. And in this case, your poles will be imaginary, just imaginary. The real part will be 0. So now we can solve it for this undamped system. You have this transfer function 9 divided by s squared plus 9. I mean, just to compare this one with the general form, we have s squared plus 2 zeta omega n s plus omega n square equals 0, or omega 0 squared. Just compare this one with this equation. We have here s squared plus 9 equals 0. From this equation, we can see that we just compare coefficient. So omega node square equal 9, which means omega node equal omega 0 equals 3 rate per second. So this is a natural frequency. So in fact, the frequency of this oscillation will be 3, right? This middle part, we don't have here s. So it's like plus 0 multiplied by s, which means 2 zeta omega node equal 0. So in this case, zeta will be 0. So the damping ratio will be 0. So when the damping ratio will be 0, you will not have this real part. Real part will not exist. You will be only, your poles will be only imaginary part. If you want to solve this one, so it will be s squared plus 9 equals 0. So s squared equal minus 9. So s equal plus minus square root of minus 9. So it will be plus minus j multiplied by 3, right? So you will have one at j3 and one at minus j3. That part, in fact, we call it omega d, in fact. Okay, so we will have this plus minus j3. So the absence of the real part in the pole pair corresponds to an exponential that does not decay. When you don't have this real part, it corresponds to an exponential which does not decay, and therefore you will keep having this oscillation. So your solution will be, after applying input and using partial fraction expansion, it will be something like this one. You will solve it, so it will be k1 plus k2 exponential minus the real part is 0. In fact, the real part is 0, so it will be minus 0t cosine omega dt plus k3. Okay, maybe we need to go back, in fact, here for the underdamped system when we have this solution, right? So we have here this solution. So the unforced or natural component, it will be k1 exponential minus theta d. I mean, your poles, you need to write your poles in this format. B1 and B2, it will be minus maybe sigma d plus minus g omega d, right? The real part and the imaginary part. If you want to write it in the time domain directly, so it will be k1 exponential minus minus sigma dt, right? Which is the exponential, the real part, cosine omega dt plus k2 exponential minus real part, which is minus sigma d sine omega dt. So it will be converted into, because it's complex conjugate. So this complex conjugate, it will correspond to this solution in the real time. And if you want to make it compact, you can just write it like a exponential minus sigma dt cosine omega dt minus phi, where a equal square root of k1 squared plus k2 squared, and phi equal 10 minus 1 k2 divided by k1, right? K2 divided by k1. So, I mean, if you want to get the time response quickly. So, in our undamped system, right, we don't have real part. So sigma d equals 0. So the solution here will be plus minus g omega d, right? Omega d will be 3. So sigma d here equals 0. So we don't have the real part. So So you need to write it in time domain, so it will be like that part. So it will be K2 exponential minus 0t multiplied by cosine omega dt plus K3 exponential minus 0t multiplied by sine omega dt, right? If you want to make it compact, so you can write it as, for example, K4 or A cosine omega dt minus phi, where phi equal tan minus 1 K3 divided by K2, right? And of course, A will be square root of K2 squared plus K3 squared. So these are formulas which you need to memorize. So this is the undamped system. So just remember that in case of undamped system, we don't have any damping effect. So in this case, zeta must equal to 0, right? And as you can see here, the response will be just cosine function. As you can see here, it's K1 plus K4 multiplied by cosine. And we don't have any exponential term here, as you can see. We don't have the damping effect because the exponential term here has the exponential part, it's 1. In fact, exponential minus 0t, it's just 1. Exponential 0t equal 1. If we have that part here, if this one exponential negative, it will have the damping effects, right? But we don't have it here, right? We don't have the part here, so the exponential term will be 1. So in this case, we will keep, the output will be function of cosine, as you can see here. The output will be function of cosine omega dt minus phi. Now we will go to the critically damped response. The critically damped response, it's like over damped, but over damped, it's we have two real poles and a distinct, two real and a distinct poles. So we have B1 and B2, which both are located on the real axis and both are different. But in case of critically damped response, both are real and repeated, right? Real and repeated. So how can we know this? So just this one, it's s squared plus 6s plus 9. So so it will be s plus 3 squared. Yeah, so we have one pole at minus 3 and another one at minus 3. So P1 and the B2 equal minus 3, right? So both are real and distinct and repeated. So to solve it using partial fraction expansion, if you remember it, we solved some problems before, so it will be like this one. So C of S will be this one multiplied by R of S, which is 1 of S, so it will be 9 divided by S multiplied by S plus 3 squared. So using partial fraction expansion, so it will be K1 divided by S plus K2 divided by S plus 3 plus K3 divided by S plus 3 squared. So it will be like this one, right? So the solution in the time domain, it will be K1, right? It will be K1 plus K2 exponential minus 3t plus K3 multiplied by t, because this one is squared, right? So it will be K3 multiplied by t exponential minus 3t. And now we need to find the value of K1, K2, and K3. So we call it critically damped. If we need to compare this one with the general form, which is s squared plus 2 zeta omega node s plus omega node square equals 0, we will see that omega node square equal 9, which means omega node equals 3 rate per second. And 2 zeta omega n equals 6. So in this case, zeta will be 6 divided by 2 multiplied by omega node, which is 3. So this one will be 1. And it's a critically damped system. So the critically damped system, damping ratio here equal 1. And just look to this real part here, it's minus 3, right? So that part, in fact, it should equal zeta omega n. Zeta equal 1, so it will be 1 multiplied by 3 equal 3. Negative, of course. So now, because we have two poles at minus 3, so we can see that, okay, we don't have any imaginary part, but we have the real part equal zeta omega n. So zeta here equal 1. So this system is critically damped. So what is the difference between critically damped and over damped? Over damped the zeta is greater than 1, right? So overdamped system. This is the overdamped system, right? We will just compare zeta value. So 2 zeta omega n equal 9. So zeta will be 9 divided by 2 multiplied by omega node, which is 3. So it will be 9 divided by 6, so it will be 1.5. So for overdamped, zeta is greater than 1. But for critically damped, zeta equal what? Zeta equal 1. And the response would be like this one, the time response. So it's two multiple poles on the negative real axis, which means your system is stable because we don't have any poles on the right-hand side. They are located in the left-hand side of the S plane. But because it's repeated, so the time response will look like this one. So the step response, if we need to summarize the step response for the second order system, so we can start with the overdamped, right? This is the overdamped system. We need to change maybe color. So this one, it's the overdamped, right? This overdamped, what is the value of zeta? It's greater than 1. And after that, we have this critically damped. And for this critically damped, zeta is zeta equal 1, right? For the underdamped system, zeta is greater than 0 and less than 1. So it's like 0.5 or something. And the undamped, zeta equal 0, right? Because it's undamped system. We don't have any real part. When zeta equal, I mean, if I need to write the poles location here, it will be like this one for this system, because the real part equals 0, because zeta equal 0. For this part, it will be complex conjugate poles. It will be like this one. For this critical damped, zeta equal 1. So in this case, the pole 0 plot, it will be real and repeated. So it will be like this one. We'll have to in the same place. When it is overdamped, it will be just two real and different, right? Distinct. So it will be like this one. So in fact, I mean, by looking into the characteristic equation of your system, you should be able to plot the time response without calculation. So this is the idea here. So just maybe it could be also a question, for example, or something like this. You have, I can give you a characteristic polynomial, or maybe not a characteristic polynomial, or a characteristic polynomial, and I can ask you to draw the response without calculation. Now we have an example here for each of the following transfer function. Write by inspection the general form of the step response. By inspection, which means we don't want to solve it in details. Right? Okay. So we need to find this one from this one. How it will look like, right? So we need to solve it for A, B, C, and D, how to get this one from this one, right? So we can start, for example, by C, because it looks like repeated. So we need 225 equal, yeah, it's 15 times 15. Yes, it could be, yes. So this one, in fact, it will be 225 divided by S squared plus, no, sorry. Need to clean it. Yes, this one will be S plus 15 squared. So C of S here, it will be 225 divided by S multiplied by S plus 15 squared. It's repeated. So in this case, C of T will be K1 plus K2 divided by S plus 15 plus K3 divided by S plus 15 squared. So, oh, sorry, this is still S. So C of T in this case, yeah, this one divided by S. So it will be K1 plus K2 exponential minus 15t plus K3t exponential minus 15t. So it will be like this. right? So it will be something like this one, and so on. You need to do it for all your examples, right? So if you cannot factorize it, try to use the law, right? If you cannot factorize it, try to use the law. Okay. So the general second order system, again, we need to revise it. The response of the second order system can be quantitatively described to a designer without the need for sketching the response. In fact, you don't need to sketch your response. Once you have the locations of your poles, it should be possible to just imagine how the response will look like. We don't care about accuracy. I just need to have a sketch of the response, approximation of the response. So the response or characteristics of the first order system can be described by time constant t, which is very easy. But the transient response or the characteristics of the second order system can be described by two variables, which is the natural frequency omega n and the damping ratio zeta. Those are very important. So as you can see, this is a general second order transfer function. It's omega n squared divided by s squared plus 2 zeta omega n s plus omega n squared. So this transfer function is characterized by omega n and zeta. Omega n, it's a natural frequency, damping natural frequency, and zeta, it's a damping ratio. A natural frequency omega n, the natural frequency of a second order system is the frequency of oscillation of the system without damping. So if we can go to the undamped system, this one undamped. So in fact, omega n, it's the natural frequency. It's the frequency of the undamped response. Do you see here? It's undamped. So the frequency of that part will be omega n. And of course, time equal 1 divided by frequency. So if the frequency here, do you see here? Here, omega n equals 3. So time will be 1 divided by 3. So it will be 0.3. So you can see that we will have one, we should have one each cycle, right? The cycle 1 divided by omega n. One complete cycle each second. Here omega n equals 3. Yeah, so do you see we have one complete cycle each periodic time. So the periodic time will be 3 seconds, right? Yeah, this one. So without damping, the poles would be on the g omega axis. If we don't have any damping, your system poles would be located on the g omega axis, and the response would be undamped sinusoidal, right? If we don't have damping, if zeta equal 0, so your poles will be located like this one, correct? Because we don't have any real part. And in this case, what will happen? So your system will be undamped. It will not damp. So it will the response will be an undamped sinusoid. The response will be undamped sinusoid. The response of the system will be, as you saw it will be something like this one, right? It will be like this. We have here an example. P divided by s squared plus es plus p. Without damping, the poles would be on the g omega axis, and the response would be an undamped sinusoid. For the poles that will be purely imaginary, we need that a part to be 0, right? Because that part, in fact, it's omega n. The general form, it's omega n squared divided by s squared plus 2 zeta omega n s plus omega n squared. If you don't have damping, the real part will be 0. So if we set zeta equal 0, in this case, that part will be 0. So the coefficient of s will be 0. So A must be 0 here. So in this case, the system will be simplified into P divided by s squared plus P. By definition, the natural frequency omega n is the frequency of oscillation of the system. Frequency of oscillation of the system. Since the poles of the system are on the g omega axis, so it will be located at plus minus j square root of P, because the poles here I mean, those poles here, it will be, we will have that part equal 0. So S1 and 2, it will be minus plus J square root of B, right? Which is equal plus minus J square root 1 minus zeta square multiplied by omega n. So if you want to get natural frequency in this case, when you don't have real part, that part will be omega n, right? So in this case, omega n will be this one is square root of, sorry, this one is square root of omega n, square root of omega n. Yeah, sorry, omega n will be square root of b, right? Sorry. Yeah, so omega n will be square root of b. Omega n will be square root of b. And remember, when it's complex conjugate for underdamped system, right? It was like that part. So we have here real part, we have here imaginary part, and we have here omega n. So omega n was the square root of the real part plus imaginary part square. You don't have a real part here, so omega n equal that part, which is the square root of b. Damping ratio is the definition of the damping ratio. It's exponential decay frequency divided by natural frequency, which is rate per second. Or it will be 1 divided by 2 pi multiplied by the natural period divided by exponential time constant. So what is the term A in the equation? 4.0. Assuming that we have an underdamped system, the complex poles have real part, which is sigma equal to minus A divided by 2, right? The magnitude of this value is then the exponential decay frequency described in section 4.4. So anyway, zeta, it will be the exponential decay frequency, which is the absolute value of the real part divided by omega n. So yeah, because I mean the real part, in fact, for the complex conjugate poles, it will be minus zeta multiplied by omega n. So the absolute of this real part, it will be zeta multiplied by omega n. We need to get omega n, we need to get zeta, so zeta will be the absolute value of the real part divided by omega n. So it will be that part, this absolute value of the real part, we call it exponential decay frequency. Exponential decay frequency, because do you remember one of the problems when we solved it, we got the sinusoidal part multiplied by exponential minus this real part, t, correct? So in fact, this is the exponential decay frequency. We call it exponential decay frequency divided by natural frequency, which is rad per second, right? So this is the definition of the damping ratio. So now we have an example. You have this transfer function. Given the transfer function, find zeta and omega n for this example. It's easy. So we'll just write it the general form. It will be omega n squared divided by s squared plus 2 zeta omega n s plus omega n squared. Just compare. So compare that part with that part. So in this case, omega n squared equals 36. So omega n equal 36. It's 4 times 9, correct? Omega n squared equals 36. So omega n, it will be square root of 36, which is 6 rad per second. So this is the natural frequency of your system. Now we need to get zeta. So 2 zeta omega n equal that part equal 4.2. So zeta will be 4.2 divided by 2 multiplied by omega n. Omega n is 6. So it will be 4.2 divided by 12 equal 0.35, right? So this is the number. And of course, now this value is less than 1, which means this system is, so what kind of system is this one? Is it underdamped, overdamped? What kind of system? we need to find zeta if zeta is less than 1, so the system is underdamped. Underdamped. So should expect that the response of the system will be something like this, because it's underdamped system. And the underdamped system, your pole location, or if we need to analyze those, we need to use the law. So your poles will be complex conjugate poles. This one delta, this one G omega. It will be like this one. This part will be minus eta multiplied by omega n. We got it already. So it will be minus 6 multiplied by this value. So it will be the real part. And this imaginary part, it will be J square root 1 minus zeta square multiplied by omega n. So now we can get the location of my poles. If you don't want to do it like this one, just use the law. So P1 and the 2, it will be minus P, which is minus 4.2 plus minus square root B square, which is 4.2 square minus 4 multiplied by AC 1 multiplied by 36 divided by B square. B square, it's 4.2 square, correct? Minus P plus minus square root 4. Okay, so it would be like this one. Just to ensure. Yes, it will be minus P plus minus square root B square minus 4AC divided by 2A. Oh, yeah. This one, 2A. So this one divided by 2A, which is 2 times 1, it would be 2, right? So it will be minus, sorry, I need to, so it will be, oh, sorry. So it will be equal. So it will be minus 4.2 divided by 2, it will be minus 2.1 plus minus, we need to solve that part, right? So that part will be 2.1. We need to find that part. So it will be, I can do calculations on my phone. So it will be 4.2 squared minus 4 times, yeah, calculator. So it will be 4.2 times 4.2 minus 4 times 36. So it will be minus 126. You need to take square root of that part. So, and divide it by 2. 4.2. $11 divided by 2. So it would be 5.62. 5.62 G. Right? So now we can find that part. So this one will be minus, this part will be minus 2.1. That part, it will be J 5.6. This one minus J 5.6. Right? So now we can find it. And this system is underdamped. Why it's underdamped? It's underdamped because zeta is less than 1, right? And therefore it's underdamped. So now we have second order response as a function of damping ratio. If you want it, so you solve for those poles using the law. So P1 and P2 or S1 and S2, it will be minus eta multiplied by omega n plus minus omega n multiplied by zeta square minus 1. If you want to get this, it's easy. So we will use the law. Just remember ax squared plus px plus c equals 0. So x1 and 2, it will be minus p plus minus square root b squared minus 4ac divided by 2a. We will apply this one here. So p1 and 2 poles, it will be minus 2 zeta omega n plus minus square root p squared, it's that part, right? So it will be 4 zeta square omega n square minus 4ac, 4 times 1, it will be 4 omega n square divided by 2a, which is just 2. So it will be, this one divided by 2, it will be minus zeta omega n plus minus This one will go out by omega n, and 2 divided by 2. So it will be square root zeta square minus 1 multiplied by omega n. If you want to make it more beautiful, so you can just say, okay, it's minus eta minus zeta omega n plus minus square j square root 1 minus zeta square omega n. So it will be a real part plus imaginary part, right? J omega n, right? So it will be a real part plus imaginary part. This real part, it will be the exponential, the real part, we call it exponential decay frequency. This real part, it's called exponential decay frequency. Exponential decay frequency. So to summarize, when zeta equals 0, your system will be undamped because the damping ratio equals 0. We don't have a real part, and if you don't have a real part, we will not have this exponential decay. Right? Again, this exponential decay frequency, we don't have any exponential decay, right? So in this case, we will not have a real part, and your poles will be imaginary, right? So you see, response will be like this one. When zeta is greater than 0 and less than 1, it's underdamped. When zeta is less than 1, this is very important, less than 1 or greater than 0 and less than 1. So it's a fraction. So in this case, we can say that your system will be underdamped and your poles will be complex conjugate poles. It will be complex and you have a real part and you have an imaginary part. If you want to get omega n will be this part. So omega n will be square root of that part plus that part. You can get omega n. If zeta equal 1, it means your system is critically damped and your poles will be real and repeated. Your poles will be real and repeated, and in this case, your response will be critically damped. When zeta is greater than 1, your poles will be real and distinct. You will have two different real, both will be located on the real axis, the negative real axis. This is real, this is imaginary. Both will be located on the real axis, and the both will be real and distinct. And the system will be overdamped. Overdamped and critically damped, both are very nice. It's very similar to the response of a first order system. This one, it's response closer to a response of a first order system. So even if you don't have the transfer function of your system and you did this mistake and you approximated it as a first order system, it's okay, no problem, because it looks like first order system, right? So we do this approximation. So usually we are working with first order system, and also you can do this mistake and you can get confused and you can approximate your second order system as a first order system if this system is critically damped or over damped. But you will see this bulge. You will be able to see this bulge. This is the difference between response of first order and second order system. If you can note, if you can, observe this one, you will understand that this system is second order system. But this is underdamped. This underdamped, it's maybe 99% of the systems which we will work with, it will perform like this one, right? And we will try to use maybe pole zero replacement to try to achieve specific performance. Last one, when zeta is less than 0, when it's negative. When it's negative, your system will be unstable because the response will just go crazy like this one all time, because it has negative damping. Negative damping means it will not damp. It will go unbounded, right? So for zeta less than 0, the system is unstable, right? Okay, so characterizing the response from the value of zeta is very important, right? So if you have a transfer function like this one, system A, for example, you need to find, what kind of system number A. So we need to write the general form of the second order system. It will be omega n squared divided by s squared plus 2 zeta omega n s plus omega n squared. And just to match coefficient. So 2 zeta omega n equal 8. 2 zeta omega n equal 8. And omega n squared equal 12. You will find omega n, it will be square root of 12. right? And from this one, you will calculate zeta. And once you get zeta, you will decide what kind of system is this one. So we will do it because this is the for system A, it's underdamped system. So we need to test it, right? So for this system, omega n will be square root of 12, which is 3 times 4. So it will be 2 square root 3 read per second. 2 zeta omega n equal 8. So in this case, zeta will be 8 divided by 2 times 2 square root of 3. Do this multiplication. Maybe you will get this value, you'll find that, okay, it will be maybe 0.3. I need to calculate this one. So it's 8 divided by 4. So it will be, this one, it will be 2. So it will be 2 divided by square root of 3. So I need to find this value. So I will do it. 2 divided by square root of 3. So it will be 1. Oh, it's 1.15, in fact. So system A here, this system A, it should be, it's greater than 1, right? So it's underdamped. System A, ABC. Okay, where is ABC? I don't know what is the connection, but maybe this one, it's for another system, right? This one, it's for another system. So this one, it will be 1.15, which is overdamped, right? We will do it for the system. So omega n square equal 16. So omega n equal 4. And 2 zeta omega n equal 8, right? So eta will be 8 divided by 2 times 4. So it will be 1. When it's 1, it's critically damped. So system B here, it will be critically damped. We will do it for that one. So omega n square equal 20. So omega n will be 2 times the square root of 5 read per second. 2 zeta omega n will be 8. So zeta will be 8 divided by 2 multiplied by 2 square root of 5. So it will be 2 divided by square root of 5. 2 divided by square root of 5, it will be, I will do it on my calculator. So it will be 0.89. So it's under 1. It's less than 1, right? When it is less than 1. So your system will be underdamped, right? This one will be underdamped. So this one underdamped. This one overdamped. This one is this one overdamped greater than 1. This one critically damped. Sorry, this one overdamped. This one will be critically damped because it equal 1 here, right? And also it's 16, so it's 4 times 4. In fact, so this one it's s plus 4 square, correct? So it's repeated and real and repeated, right? So this one it's 12. It's 3 times, it's 2 times 6. So it will be s plus 2 multiplied by s plus 6. So real and distinct, right? So this one will be overdamped. This one will be critically damped because poles here are real and repeated, right? This one will be complex conjugate because it's underdamped system. So now we can solve many systems. So please try to go to this skill assessment exercise and solve it. So we need to find the value of zeta and omega n for this example, and I try to characterize the nature of the response. Characterize means you need to say if it is underdamped, overdamped, critically, or undamped. So the general second order step response, if you want to get the step response. So this is my system, right? So input is R of S, the output is C of S. This is a transfer function, which is omega n squared divided by S squared plus 2 zeta omega n S plus omega n squared. So you want to get the time response or the step response. Step response, it's the time response for a step input. So now we need to get C of S. So C of S will be this transfer function multiplied by R of S. And R of S for step input, it will be 1 divided by S. So it will be omega n squared divided by S multiplied by that part. That part, we assume that it's complex conjugate. So to solve it, we solved an example similar before. So we'll use partial fraction expansion. We assume that this one is complex. So in this case, we will leave it as it is, but we will define that part as K2S plus K3, and we will solve it, and we will go to the inverse Laplace transform table, try to find something from here which is closer. So it will be this solution. And you can simplify it by getting this one. It will be a exponential, do you see? Minus zeta omega n. So in fact, this one, it's a, you can say that it's K1 plus a exponential, the real part, minus zeta omega n t cosine omega dt minus phi, where phi will be 10 minus 1 zeta divided by 1 minus zeta squared, right? So this is the real divided by imaginary part. So the second underdamped response for different values of zeta. I mean, we know that for underdamped system, zeta will be a number between 0 and 1. When zeta is small, for example, when it is 0.1, what will happen? The system will take more time to settle down. You see, it will take more time because it will damp with small fraction. For damping ratio, the damping ratio is small, so it will take more time to damp, correct? Because it's 0.1. When you compare it with 0.8, which is close to 1, what will happen? The response will be very close to a response of maybe a second order, first order system, because when it's 0.8, it will damp very quickly, right? So this damping ratio is very, very important. And as I told you before, this damping ratio, you can discover its impact from the real part. When damping ratio equal 0.1, when it's a small, it means your complex conjugate poles will be very close to the imaginary part, the imaginary axis, G omega axis. Because this is the real part, which equal eta minus eta multiplied minus zeta multiplied by omega n, right? When it's large, like 0.8, you will go far away from the G omega axis. And in this case, what will happen? Your system will be faster. When you are far away from the G omega axis, what will happen? The system will be faster. So it will settle down very quickly because settling time will be shorter, right? The settling time, and it's the same as we did with the first order system. It is the same. When the first order system has a pole which is far away from the G omega axis, the time constant will be shorter because the time constant will be 1 divided by A. When A is large, what will happen? T will be very small, so the time constant will be very small, so the system will be very quick. So for example, if I can give you an example, you have a motor, DC motor and boiler. So which one will have a time constant closer to the G omega axis? Maybe one will have a pole here, and one will have a pole very far away from the G omega axis. Which one? Which one will be a motor and which one will be boiler? Just imagine this is A, and time constant will be 1 divided by absolute value of A. So when A is large, T will be very small. So this one will be faster, this one will be faster. This one will be slower. Of course, this one will be the boiler or heater. This one will be maybe the motor, correct? So the motor will be much faster than the heater. Time constant of the heater, it takes too much time to go. I mean, to heat your water from 0 to 36 degrees Celsius, for example, it will take much more time than a motor. Motor will be much faster. Maybe it will reach high RPM much quicker than the heater. So the parameters of the second order system, we have two sets of parameters, two parameters which are associated with the second order system. Those are the damping ratio and natural frequency. Those are the two parameters which are used to characterize the second order system. There are some other parameters which are associated with the underdamped response. This is, in general, in fact, those damping ratio and natural frequency, those are two parameters which are associated with any second order system. But there are some other parameters which are associated, especially with the underdamped response, such as rise time, peak time, percent overshoot, settling time, which are used to describe the transient or natural response of the second order system. So if we can do it like this one, so it must be underdamped. Otherwise, we will not be able to get those numbers. So we need to get this peak time. This one will be the peak time, call it P. We have percentage overshoot, right? This one will be percentage overshoot. Could be 10%, 15% of the final value. Settling time, TS, correct? And also maybe transient time. What is the rise time? The rise time, it's the rise time. This is the time which the system will use to go from 10% to 90% of the final. This one will be the rise time, TR. And we agreed last time that rise time equal 2.2 time constant. Settling time is around 4 time constant, right? So those are the parameters which are associated with the time response of your second order system. So we have parameters associated with the general second order system, which is the damping ratio and natural frequency, and also we have some other parameters which are associated with the response of the underdamped response. Because if your system is overdamped, we don't have those, we don't have any overshoot. If your system is overdamped, so it will be like this one, like first order. We don't have overshoot, we just have here maybe rise time, settling time. We don't have peak time, right? But we will have a settling time. We will have also maybe rise time, correct? Time constant we have, but we will not have overshoot or peak time. So those parameters are associated with the underdamped response of the second order system. So second order underdamped response, if you need to see it, so this is the final value. We have here a final value. We have here final, this is my final value, which we need to reach, or the set value, for example. And we have this peak value, this is the peak time. Peak time, we will have it when we have the maximum peak. And the difference between C max and the C final, it will be max overshoot. This one will be percentage overshoot, right? We need to overshoot. We need to go above the final value by 10% or 15%. When your response are within plus minus 2% of the final value, it will be settling time, right? So the settling time, it is the time which is required to be within plus minus 2% of the final value. So when you reach 98% of the final value, you can say that now we are in a steady state. So that part will be a transient response. And the response here will be steady state response. Correct? So how can we define it? When our response are within plus minus 2% of the final value, or 98% of the final value, we can say that now we are in a steady state. So this is the settling time. Remember, settling time equal 4 time constant. Peak time, it is the time at which we will have the maximum overshoot, right? Rise time, it is the time which is required to go from 10% to 90% of the final value. This one would be the rise time, and this rise time equal 2.2 time constant. Time constant, it's the time which is required to go from 0 to increase from 0 to 36% of the final value, right? We will call this one time constant, right? This one will be time constant. So from the response, you will be able to measure those values. So in fact, if you have the characteristic, if you have the transfer function of your system or differential equation, we will be very, very happy for this. If you don't have this, you need to use identification. So you need to use this step response. So I need to step input to my system, plot the response, and from this response, we will be able to get identify the transfer function. So we have some definitions. We did that before, but we can repeat it again. What is rise time? It's the time which is required for the waveform or the response to go from 0.1 to 0.9 of the final value, 10% to 90% of the final value. Peak time is the time which is required to reach the first or the maximum peak. Percent overshoot, it's the amount that the waveform overshoots the steady state or final value at the peak time, expressed as a percentage of the steady state. Settling time is the time required for the transient damped oscillation to reach and stay within plus minus 2% of the steady state value. So those are the definition of those parameters. In the design, if we need to design a controller, so we need to look into rise time, peak time, settling time, because it will give us information about the speed and the shape of the transient response. This information can help a designer to determine if the speed and the nature of the response do or don't degrade the performance of the whole system. As an example, the speed of an entire computer system depends on the time it takes for a hard drive head, for example, to reach a steady state and read data. I mean, if you need to, maybe in all the days, for example, because before we have those hard drives, which are mechanical and magnetic. So we have this head or the floppy disk, floppy drive. So you have a head, you have a motor, and it need to, when you want to store something in your floppy disk, for example, so you need to just order it, and it will take time for the motor to move the head and start printing stuff on the magnetic disk, for example. So it takes time. So it will add to the overall maybe time constant or delay time of your system. Passenger comfort, for example, depends on the suspension system of a car and the number of oscillations it goes through after hitting a bump. After hitting a bump, you will have some oscillations. So the number of oscillations, it will impact degree of comfort of the passenger. There are some formulas for calculating peak time, percentage overshoot, settling time as a function of zeta and omega. And so the most important is to find the damping ratio and the natural frequency. Once you have damping ratio and the natural frequency, you will be able to calculate all other parameters. So for example, if we need to get the peak time, so peak time will be pi divided by omega n multiplied by y minus zeta square. In fact, this one, it is an imaginary part. This is the imaginary part of your complex conjugate pools. Those are my complex conjugate pools. This is J square root 1 minus zeta square multiplied by omega n. So the amplitude of this imaginary part, it's that part. So pi divided by that part, it will be the peak time. Percentage overshoot, it will be exponential minus zeta pi divided by y minus square divided by 1 minus zeta square multiplied by 100, right? So in fact, it's that part, real part divided by the imaginary part, right? Because this one, it's minus zeta omega n. So just divide that part by that part, right? Divide that part by that part. So omega n will cancel omega n, so it will be multiplied by pi. So it will be pi multiplied by zeta divided by 1 minus zeta square. And you need to multiply it by 100 to be in percentage. So this is the percentage overshoot as a function of zeta. If you have the overshoot, for example, if overshoot is given, how can we find zeta? Because I can tell you, please, I need to design a controller to achieve 10% overshoot. So in this case, from those 10% overshoot, we need to find zeta. So how can we do this? So just to take len of both sides from this equation and try to solve it for zeta. So zeta will be minus len, multiply len of percentage overshoot divided by 100. So divide both sides by 100 here. So cancel that one from that side, take len of both sides. So it will be minus eta pi divided by square root 1 minus eta square equal len len percentage overshoot divided by 100, right? So now we need to find zeta, multiply both sides, square, right? So square both sides, so it will be zeta square pi square divided by 1 minus zeta square equals this len square. I will call it len square, right? To simplify. Cross multiply and solve. So zeta square pi square plus zeta square multiplied by ln square equal this ln square. Take zeta square as a common factor, so zeta square will be ln square divided by pi square plus ln square, right? Take square root of both sides, so zeta equal square root of there is something, I did something wrong here, so we will square, so it will be zeta square by 1 minus zeta squared. Yeah, so no problem, just take square root, so it will be ln square, square root of ln square, it will be just ln divided by square root of that part, right? So it will be zeta. But this negative sign, so it will be this one cross multiply. We'll come here by positive. So this one is okay. Yes. So we need to revise it to know why we have here negative, right? So it will be minus zeta pi divided by 1 minus zeta square equal ln percentage overshoot divided by 100. So cross multiply, so it will be, yeah, we have here minus. I forgot about this minus, in fact. Sorry, I forgot about this minus here. I did a mistake here. So we have here minus. So multiply both sides by, okay, so it will be minus zeta by square. This one we have here minus. Will come by positive. So it would be, it will be solved if we just multiply here by negative. So this one will be plus, this one will be negative, right? Anyway, we need to revise this one. So anyway, you have this relationship between zeta and the percentage overshoot. So if you want specific percentage overshoot in your system, what will be the zeta value for doing this? It's a design parameter, for example. So what is the damping ratio? So we have this curve, because this equation, it's difficult to solve. So we have this graph, which plots the relationship between the damping ratio and percentage overshoot. So if you want to have 20% overshoot, what would be the damping ratio, for example? If we need to have 20% overshoot, just find this value. So this one will be, maybe it's 4. So zeta here will be maybe 0.49, right? So from this curve, in fact, we will be able to find the zeta, which will help us to get maybe 20% overshoot. Of course, if you want to higher percentage overshoot, what does this mean? In fact, we need to decrease zeta, correct? For example, zeta here equal 0.1. And this is in fact identical with this graph. Do you see? When zeta is small, you will be able to get very large overshoot. Very, very large. When zeta equal 0.1, you can get, the final value is 1, and we can go to 1.8, which means we can get 80% overshoot. If you want to get maybe smaller overshoot, maybe around 20%, so it should be 0.5. So as you can see here, in fact, it corresponds to this figure very well. So yes, here it's 80%. If you want to get 80%, you need to select eta equal 0.1. So we have this graph. From this graph, you will find is a damping ratio for specific percentage overshoot. If you want to calculate settling time, so the settling time will be 4 divided by zeta omega n. This is the real part. In fact, this is the absolute value of the real part. It will be 4 divided by zeta omega n. This is the settling time, which is 4-time constant, right? And the time constant, it's 1 divided by the real part in reality, right? Rise time, there is no precise analytical relationship between the rise time and the damping ratio. There is no relationship. So in this case, there are some tables which are used for finding zeta for special if you need to achieve some rise time. So we have this graph here, and it's the ratio between relationship between the damping ratio and normalized rise time. So in y-axis, we have here rise time multiplied by natural frequency. This is the rise time multiplied by natural frequency. And on this ratio here, in this x-axis, we have the damping ratio. We need to find the damping ratio. So we need, if you need to achieve some certain rise time, multiply it by the natural frequency, and you will get maybe this zeta value, right? Which can help you to get this rise time. So we need to take an example. So we have this example. We need to find peak time, percentage overshoot, settling time, and rise time. First step, if you need to solve for those, we need to get first zeta and omega n. So this one, in fact, it's called equal omega n squared divided by s squared plus 2 zeta omega n s plus omega n squared, just by matching coefficient. So omega n squared equal 100, which means omega n equal 10 rate per second. We got natural frequency. 2 zeta omega n equal 15. So in this case, zeta will be 15 divided by 2 times omega n, which is 2 times 10. So it will be 15 divided by 20. Simplify, divided by 5, it will be 2. Divided by 5, it will be 3. So it will be 3 divided by 4, which is 0.75. Zeta is less than 1, greater than 0, which means my system is under-damped. Your system here is under-damped system, correct? So the response of the system should be like this one. Now we need to get the peak time. This is my peak time. So what is the peak time? We will go to the formula. How can we get the peak time? Peak time equal pi divided by omega n multiplied by that part. So just substitute into that part. So peak time equal pi divided by omega n multiplied by 1 minus eta squared. So it will be pi, which is 314, divided by omega n. What is omega n? It's 10, multiplied by square root of 1 minus zeta squared. What is zeta squared? It's 9 divided by 16. 9 divided by 16. So it will be 3.14 divided by 10, multiplied by this one would be 16 minus 16. So it will be so it will be square root of 7 divided by 16. Yes, it will be something like this one. So you will do the calculation and you will get, it will be this number, seconds. So in fact, you can say that it will be 4 times 3.14 divided by 10 multiplied by square root 7. I need to do this calculation to check that numbers are correct. So I will do it. So it will be 4 times 3.14 divided by 10 divided by square root of 7. Yes, so correct. So it will be 0.4747, right? Just try to round it to the nearest integer. So it will be 0.0475. So it will be this number, second. So this is my peak time. We need to get the overshoot. How can we get the overshoot? To get this maximum overshoot, we will go to this formula. Maximum overshoot, it will be exponential minus zeta. I have zeta, we have pi. So just substitute in this equation. You will be able to get this maximum overshoot. Settling time will be pi divided by, it's 4, settling time is 4 divided, or pi divided by the real part, right? It's that part. So yeah, it's 4 divided by the real part, zeta omega n. 4 or pi, in fact, right? So we will see how it is calculated here. Okay. What is the example? Yes. Yes, this is the example. We need to get settling time. So settling time, it will be pi divided by zeta multiplied by omega n. So it will be 3.14 divided by zeta is 3 divided by 4 multiplied by omega n, which is 10. So it will be, yes, I will do it in my calculator. So it will be 3.14 divided by 10 divided by 0.75. Yes. In fact, it's not pi, it's 4 divided by, not that part, it's 4 divided by that number. So I will do it one more time. So it will be 4 divided by 10 divided by 3 multiplied by 4. Yeah, it will be that number. So this is correct. So it's a 4 divided by this one, not pi, it's 4, right? Normalize the right, we need to get the rise time also. We need to get this rise time. So we need to use a table in figure. Normalize the rise time is approximately 2.3 seconds. 2.3 seconds. We will get the normalized first rise time. We will go to this table, rise time, normalized rise time. We need, what is the damping ratio here? What is the damping ratio? It's 0.75. 0.75. 0.75. So it will be this. It will be maybe 2.3. 2.3. Yes. Normalized rise time is approximately 2.3. So this normalized rise time, it will be as you can see here, it's 2.3, right? 2.3. 2.3. We will divide it. This is rise time multiplied by natural frequency. If you want to get rise time, so it will be 2.3 divided by omega n, which will be 2.3 divided by 10, 0.23 seconds. So this one will be my rise time, 0. Yeah. So now this is my rise time. So this problem demonstrates that we can find peak time, overshoot, settling time, rise time without tedious task of taking an inverse Laplace transform or plotting output response and taking a measurement from the plot. It's very, very easy, right? So the most important here is that you will start solving your problem from the transfer function. From this transfer function, you will get zeta and omega n. Once you have zeta and omega n, you have formulas for calculating peak time, percentage overshoot, settling time, and also rise time. Rise time, you will get it from the table, from the figure. Right? We need to get normalized settling rise time, and after that we will divide it by natural frequency to calculate rise time, right? Actual rise time. Yes. So peak time and percentage overshoot. Settling time, rise time in terms of pole location. We need to know, we need to understand this in terms of pole location. So we studied expressions which relate peak time, percent overshoot, and settling time to the natural frequency and the damping ratio. So to do this, you need to start from the transfer function. From this transfer function, you will get damping ratio, zeta, and the natural frequency, omega n. And we have formulas, equations, for calculating peak time, percentage overshoot, settling time, and rise time. Now let us relate these quantities to locations of the poles, which generates these characteristics. We need to locate those to the pole locations, because in fact, one of the most important design approach which we will use in this course, is pole zero placement. So we need to replace or reallocate our poles into locations which will achieve the desired performance. To demonstrate the relationship between the pole location and the specifications of the second order underdamped response, we will start by this one. So we have your second order system, it's underdamped. So this is the complex conjugate poles of underdamped system. This system is underdamped, right? Underdamped second order system. We have the real part. The real part, it will be minus zeta omega m, which will be minus sigma d. It will be minus sigma d. It's called exponential damping frequency, something, that part. And we have this imaginary part. It will be omega d. It will be plus minus g square root 1 minus zeta square multiplied by omega n. So we will call this one j omega d. So that part, we will call it omega d. That part, we will call it sigma d, the real part and the imaginary part. You can get the omega n natural frequency here. You can get also angle phi here, right? Or so the radial distance from the origin to the pole, this radial distance from the origin to the pole is the natural frequency. We can get this one as a natural frequency. Once you have this one, you can measure this angle, and the cosine of this angle will be the damping ratio. So once you have theta, you can get this theta angle, and the cosine of this angle will be zeta, because in fact the cosine, it's that part divided by that part. So it will be minus zeta omega n divided by omega n, right? So it will be zeta. So cosine of this angle, if you can measure theta, cosine of zeta will be your damping ratio. Omega d is the imaginary part of the pole and is called the damping frequency of oscillation. Omega d, we call it damping frequency of oscillation. Damping frequency omega d is the imaginary part of the pole, and it's called damping frequency of oscillation. So in fact, we can just write our poles P1 and 2. It will be minus delta D plus minus J omega D. Omega D, we call it damping frequency of oscillation. Sigma D is the magnitude of the real part of the pole, and we call it exponential damping frequency. So this one exponential damping frequency, this one damping frequency of oscillation, right? So we have real part and imaginary part. The real part, we call it exponential damping frequency, and the imaginary part, amplitude of the imaginary part, we call it damping frequency of oscillation. Once you have those, we can try to link it with the formulas, right? So for example, the big time was pi divided by that part. That part, it's the damping frequency of oscillation. It's omega d. It's pi divided by the absolute value of the imaginary part. So it will be pi divided by omega d. This is the peak. So pi divided by that part, it will be the peak time, right? It will be the peak time. Pi is constant, so TB is inversely proportional to omega d. So if you increase omega d, TB will decrease, correct? And if you decrease omega d, right, TB will increase. So in this case, if I can compare it with a system here, for example, which one will have bigger peak time? So you can see here, we will divide here pi divided by this omega d. Omega d will be larger. So in this case, peak time will be smaller, will be shorter. So the system will be faster. So if I can do it like this one, you have a system with peak value like this one, and a system with a peak value like this one. So we have here two peak value, TP1 and TP2, right? TP2. This one will be TP1 because it's faster. This one will correspond to TP2, right? Why? Because peak time will be pi divided by omega d. When omega d increases, TP will decrease, and vice versa. For the settling time, it will be 4 divided by omega d. It will be 4 divided by the real part. So this is the settling time. So also, if the real part will increase, the settling time will decrease, which is good, right? Because the system will be faster. So if we can take those away from that location, if we can get it here, for example, if we can get those here. So in this case, if we have a settling time for this one, TS1, we will get here TS2. In fact, TS2 is less than TS1, right? TS2 is less than TS1. Here also TP1, it will be less than 2P2, TP2, correct? So in this case, we know how can we reallocate our pools in the complex S-plane to achieve the desired, design requirements. So peak time is inversely proportional to the imaginary part. Peak time is inversely proportional to the imaginary part of the pool. Settling time is inversely proportional to the real part of the pool. So peak time, it will be pi divided by omega t. Settling time, it will be pi over 4 divided by delta d. So it's just, we did that already. Zeta called zeta also damping ratio, it's cosine theta, cosine this angle, right? So the radial line are lines of constant damping ratio. I mean, if you have those radial line, if you will move across a line, this line will be a line of constant damping ratio because it has the same theta. So if I can compare this line with this line 1 with line 2, each line has a constant damping ratio because the damping ratio will be cosine theta. So if you will move across this line to infinity, you will have the same damping ratio. So if you have your pools here, for example, if you have your pools here, what will happen? For this pool, you will have a peak time, specific peak time. It will be TP1. What is the peak time here? It will be pi divided by omega t. So this peak time, it will be pi divided by omega d. It will have also a settling time. This one will have a settling time. I mean, this location here, we will have here a settling time, right? This settling time, we will call it maybe TS2, for example. It will be, maybe it will be pi divided by delta D, right? So the percentage overshoot is only a function of, overshoot is function of zeta. So the radial lines are lines of constant overshoot. So if you will go across this line, you will have constant overshoot all time, right? Because if we go to the equation of percentage overshoot is function of zeta, right? So this radial line, it's a line with constant damping ratio. So if you will move across this line, you will have the same percentage overshoot. Yes. So this line has percentage overshoot fixed. This line also has a percentage overshoot which is fixed because it's proportional to zeta, or a function of zeta, and the zeta is cosine theta. Vertical line on the S-plane are lines of constant real value. I mean, if you have those vertical lines, those vertical lines are lines with constant real value. This line, for example, it's a line with constant real value. This line, it's a line with constant real value. And those real values are connected with the settling time. So those lines are lines of constant settling time because the settling time here, it will be pi divided by delta D. For TS2, it will be pi divided by delta D2, for example, right? So those vertical lines are lines with constant real value or lines with constant settling time. We still have the horizontal lines. Those horizontal lines on the S-plane are lines of constant peak time because the imaginary part here is constant. The imaginary part here is constant, and the peak time will be pi divided by omega d. So in this graph here, this is the connection. So radial lines are lines with constant overshoot. Horizontal lines are lines with constant peak time, and vertical lines are lines with constant settling time. We have some notes here, moving the poles up and down. If you want to move your poles up and down in the vertical direction, it will keep the real part the same. If I have, for example, this graph here, look into this graph. I have my poles at location 1. If I will move it from location 1 to location 2, or from location 2 to location 3, what will happen? In fact, the real part will be the same all time. And if the real part is the same, it means your settling time will be the same. So TS will be the same all time, which is pi divided by delta D, or sigma D, right? So the settling time will be the same all time. So moving the poles up and down in the vertical direction, keeping the real part the same, the frequency increases, but the envelope remains the same since the real part of the poles is not changing. You will change the frequency, correct? You will change the frequency because natural frequency increase or omega D will decrease. I mean, if you go across this line, delta D will be fixed, but the imaginary part will decrease. So here we will have G omega D1. Here we will have another G omega D. And omega D, in fact, it's the damping natural frequency, right? So what will happen? You will keep this envelope the same because this one, in fact, it's function of exponential minus delta dt. dt is fixed, so you will keep the same envelope, right? You will keep the same settling time. Your system will settle down in the same time. But what will change here? What will change will be the damping frequency, natural frequency. This one, omega d. And what is omega d? In fact, omega d is connected with a peak time, because peak time will be pi divided by omega, right? So when omega d increases, so for location number 1, maybe we will have peak time here. This is TP1. If you will increase omega d, what will happen? TP will decrease a little bit. So in location number 2, it will be a little bit smaller. So we will have the maximum peak here, 2TP2. If you will keep increasing it to location number 3, what will happen? It will decrease more. So your system will be faster. So we will get TP3 here. So you will change the peak time. So if you want to design a maximum overshoot with maybe, or a peak time, for example, I need to get the maximum peak at that time. You can design it exactly when you reallocate your poles to some specific locations to achieve this specific design requirement. So, so here, if we will keep the real part the same, so the envelope will stay the same because this envelope is function of exponential minus delta dt. It will stay the same, but what will change here? It will be the natural frequency, right? It will increase. When it's increasing, what will happen? The peak time will decrease. You can ask me, but the overshoot, we can see that the overshoot is increasing, right? Yes, because also when you take it up like this one, this real part, it will be zeta. Yeah, theta will decrease, will change. I mean, we have this zeta equal cosine theta. So for this line, we will have a theta value. For this line, we'll have another theta value. This one will another zeta value. So the each one will have different maximum overshoot. 1, overshoot 2, maximum overshoot 3, right? Because theta will change. So all curves fit under the same exponential decay curve, which is the envelope. The settling time is virtually the same for all waveforms. Of course, the settling time will be the same because the settling time is maybe pi or 4 divided by delta D. So delta D is the same. So 4 divided by the same value, you will get the same settling time. So settling time will not change. Notes number 2, moving the poles left and right in the horizontal direction. If we have this horizontal direction, if we are moving the poles in the horizontal direction, we will keep the imaginary part will be the same, right? So omega D will be the same, which is a damping frequency. So you will have the same damping frequency. As the poles moves to the left, the response damps out more rapidly. while the frequency remains the same. The frequency will be the same because omega d will be the same, right? But what will happen here? It will damp more rapidly while frequency remains the same, right? So we will be able to reach settling. I mean, for the system 1 and system 2, for example, system 1 and 2. For system 1, we will have this, the envelope will change, in fact, right? So we have here theta. We have here this real part. So we will get this envelope for this system. If you will go to location number 2, the real part will increase. We will have another delta sigma d, for example, which will increase. So what will happen? We will get a faster, we will get 1 and 2. Okay, so this is 1 and this is 2. So this one will be exponential minus delta d. This one will be exponential minus maybe delta d, maybe 2, for example, t, right? So when the exponential part, when the real part decreases, what will happen? Your system will decay faster. It will damp out more rapidly. So system 2, it will damp out more rapidly. And in this case, your settling time will be much less, correct? So it will settle down much faster because the settling time equal maybe 4 divided by delta E. So the peak time remains the same for all waveforms because the imaginary part. If we need to check, this is a peak value and this is peak TP. What is TP? So to be, it will be pi divided by omega t. Omega d is the same, so the peak time will not change. But the maximum overshoot will change. Why it will change? Because for location 1, we will have theta 1, and we will get eta 1. It will be cosine theta 1. For location number 2, we will get another zeta, right? Which will be cosine another theta 2. And the theta is connected with the overshoot. So in location 2, zeta will be much larger, right? Because theta will be smaller, so we will get much larger. Cosine theta will be much larger. So it will damp much faster than system in location 2. It will damp faster than location 1. Notes number 3, moving the poles along the constant radial line. We have this radial line. For this line, in fact, we have the same theta. So zeta will be the same. Zeta will be the same. So what will happen here? So we will have the same maximum overshoot. We will get the same maximum overshoot, the same maximum overshoot, the same maximum overshoot. But what will change here will be, the maximum overshoot will remain the same. So the response look exactly alike except for their speed. The response is the same, but the speed will be different, right? So what happened here? We will get the same maximum overshoot, but because zeta is the same. But here, when the omega d increases for system 1, for example, we will have settling time and rise time, right? We will have settling time and rise time. When we go to location number 2, what will happen? Settling time and rise time will decrease. When we go to location number 3, settling time and rise time will decrease, which means the system in location number 3 will be faster. But you will get the same maximum overshoot. About the peak time is so the peak time, it's pi divided by omega d, right? Yes. Peak time is pi divided by omega. So for system number 1, peak time TP will be pi divided by omega t. We will get this peak time. When you go to location number 2, omega d will increase, so peak time will decrease a little bit. So it will be here. When you go to location number 3, omega d will increase more. So in this case, TP will decrease little more. So it will be in that location. So 2p3 will be less than 2p2, less than 3p1. So now we have an example. You have this system given the pole plot shown in figure. We need to find zeta. omega n, peak time, overshoot, and settling time from this graph. So how can we do this? We have theta, right? From this theta cosine theta, it will be zeta. I mean zeta damping ratio, it will be cosine theta. And we need to find theta. So we know this distance. In fact, this one it's minus. This one it's minus 3. This one it's omega d, which is 7, right? This one 7. This one 3. So theta will be 10 minus 1, 7 divided by 3. We will see, or yeah, it will be cosine. Cosine 10 minus 1, it will be cosine theta. I mean, theta is cosine theta. What is theta? Theta, it will be 10 minus 1, 10 minus 1, 7 divided by 3. So if you want to get damping ratio, so damping ratio, it's cosine theta, right? So what is theta? We need to find the theta. So theta will be 10 minus 1. This one divided by this one, 7 divided by 3. So we need to get 5 to get find theta. So 10 minus 1, 7 divided by 3, and after that you will take cosine of this one, so it will be zeta. So theta, it's this number, which is greater than 0 and less than 1. So my system will be underdamped system. We need to find natural frequency. So natural frequency will be this distance, right? So it will be square root. It will be square root this one plus this one. So it will be square root 9 plus 49. 7 square plus 3 square. So it will be this now number rate per second. Now we have zeta and omega n. We need to get peak time. So the peak time will be pi divided by omega d, which is pi divided by 7. It will be this number. Percentage overshoot or percent overshoot, it will be exponential minus pi zeta divided by square root 1 minus zeta square multiplied by 100, so it will be 26%. Settling time, it will be its approximate settling time. It will be 4 divided by the real part, or pi divided by real part. It's 4 divided by real part. Real part is 3, so it will be 4 divided by 3, so it will be 1.33 seconds. So now if I need to plot the response of my system, we have here 26% overshoot, so it will be something, right? It will be like this one. This is the peak time. Peak time equal 4.5 seconds. Settling time, it's 1.3, something here like this. TS 1.33 seconds. Maximum overshoot is this one, 1.26. 1.26, it would be like this one. So now we have the peak time, we have the settling time, we have omega n and zeta. So we can get all those numbers from the location of my of the pool plot. Now we have a design example. In this example, we need to you have a system shown in figure. Find J, D to give you 20% overshoot and settling time of 2 seconds. It's a design, in fact, settling time of 2 seconds for a step input of a torque T of T. So I mean, this system, it has a torque. We apply a torque here. When we apply a torque here, this one maybe it's a motor, right? And we need to apply a torque here to rotate it. And we need to get 20% overshoot and a settling time of 2 seconds. So it's a system, and we don't have any differential equation. And we need to select what kind of what J, what D damping. This number, for example, it has a damping factor or D equal D. So how much should we buy? I mean, if we need to buy our system to achieve those results. So how can we select those design parameters, for example? So this system, it's a system, we don't have any differential equation to describe it. So first we need to derive its transfer function in terms of J and D. And then we need to compare it to standard second order differential equation. After that, we will find the theta and the omega n. From the theta and the omega n, we will try to we will compare it with this one. So, and after that, we will try to find zeta and omega n, which will give us those 20% overshoot and settling time of 2 seconds. So now we have this overshoot, percentage overshoot equal 20%, so 0.2, right? We have an equation which is exponential minus pi zeta divided by 1 minus zeta squared multiplied by 100, correct? So from this equation, we will find zeta, which will give us percentage overshoot of 20%. And after that, from the settling time, we know that Ts equal 4 divided by delta T, which is zeta omega n. We know that this one is 2 seconds, right? Cross multiply, so zeta omega n will be 4 divided by 2, it will be 2. Once we find the zeta, we can find omega n, it will be 2 divided by zeta. So from this equation, we will be able to find omega n and the zeta. Once you have zeta and omega n, which will give you this response, you will compare the equation which you obtained as a function of g and d with this one, and you can find the value of g and d, the optimum values, which will give you the desired response. So we will solve it first. So first, we need to find the transfer function of the system. It will be like this one, and it's a second order. You compare it with a second order differential equation. So it will be omega n squared divided by s squared plus 2 zeta omega n s plus omega n squared, just to make comparison. So omega n squared equal k divided by j. So omega n will be square root of k divided by j. 2 zeta omega n equal d divided by j. So in this case, I have here omega n, so it's okay. Now we need to find the zeta from this equation, right? But from the problem, we know that settling time equal 2, so it will be 4 divided by 2 zeta omega n. So in this case, zeta omega n will equal 2. So 2 zeta omega n equal, because 2 zeta omega n equal 2, so substitute into this equation. So 2 times 2, it will be 4. So d divided by g equal 4, right? So now we have two equations. We have this equation. I can square it, in fact. So k divided by j equal omega n squared. And I have here d divided by j equal 4, correct? If you can just divide those two equations, divide this or multiply or whatever. So we can get, we can solve it for d and j, right? So dj equal 4, d divided by g equal 4. So we can say that, okay, d equal 4, d equal 4j, for example. This is one equation. Substitute into this equation by this value, d equal 4j. So here. So zeta will be 4 divided by 2 zeta omega n, which equals 2 multiplied by square root g by k. For 20% overshoot, we will find the zeta. So zeta will be this value. Substitute this value here. So we will find the square root of g divided by k equals this one. Square it and divide by 2. So j divided by k will be this number. So now we have this one. This is one equation. And we have also this equation, correct? So from the problem, it was given that k equal this 5 newtons. We have here k equal this one. So substitute this one into this equation, right? We will get g. So j divided by k equal this number. I know k, for k equal this number. So j will be this number. So now we found j. So found the specification, in fact. If you can find the j, we will go back to this equation here, d divided by j equal 4, or d equal 4j. From this one, we can get d. So d, it will be 4 times this number. It will be 1.04 Newton meter second per radian, for example. So now it's a design, in fact. So now, if you want to buy a system, if you want to buy a component, you can just buy maybe this motor with this coefficient and the damper with this coefficient in order to get this performance, 20% overshoot and settling time 2 seconds. Maybe if you will buy other components, you will get different response. So now it's design, right? We try to design to achieve some desired response. So in fact, maybe I would like to maybe stop here, or we can just continue that part. So it's a second order transfer function by testing. I mean, we did that in fact for the first order system. So do you remember if you have a first order system, you don't know the transfer function, how it look like. You just need to apply a step input to your system, plot the response, and from this response, you will be able to find the time constant. And once you know the time constant, you will be able to find A, the system bool. So if you can remember, for a first order system, it was transfer function, it was like K divided by S plus A. We will apply here step input, Bu of S equal 1 divided by S, and you will get the output, which is C of S. It's identification. And you will plot the response of your system, and you will get the time constant. We will get this time constant, and from this time constant, we will get A, because A will be 1 divided by T. And from the steady state value here, you will find, because this is steady state value, in fact, it's K divided by A. Once you have A, and you know this value from the graph, you will be able to find the K. So in this case, you can find the parameters of your first order system. You can do the same for the second order system by testing, if we need to find the transfer function by testing. So we have here a system. You have transfer function, and also this transfer function, you need to find zeta, omega n, settling time, peak time, rise time, percentage overshoot for this system. Of course, this is easy, because this one, we will equate it with the general form, which is omega n squared divided by s squared plus 2 zeta omega n s plus omega n squared. By comparisons, omega n squared equal 361. So omega n in this case will be square root of 361, which will be 19, right? I will try double check with my calculator. So it will be 361 square root. So it will be 19. This is okay, rate per second. We will compare also that part. So 2 zeta omega n equal 16. So zeta will be 16 divided by 2 multiplied by omega n. Omega n is 19, right? So 16 divided by 19. 16 divided by 19 divided by 2. It's 0.42. 0.42. It will be 0.421. Right? So you will get this number. This number, it's greater than 0, less than 1. So your system is under damped. Now we need to find settling time. So remember that we will start with the peak time first. What is the peak time? So peak time will be pi divided by omega d, which will be pi divided by square root 1 minus zeta squared multiplied by omega n. Substitute and get this value. You will get the peak time. Settling time, it will be 4 divided by delta d. So it will be 4 divided by zeta multiplied by omega n. You will get the settling time. Rise time, we need to get it from the graph, right? For zeta, we will go back to the graph. We can do it quickly also. Zeta is 0.42. We will go back to the graph. 0.4 to 0.4, so something like here, correct? So we will try to get approximately, so it will be 1.5. 1.5, just remember, divided by omega n. 1.5 divided by omega n. 1.5. 1 point, so TR, it will be 1.5 divided by omega n. Omega n is 19, so it will be, I will do it by my calculator. So it will be 1.5 divided by 19. So it's very good, 0.0789 something. So it's exactly the same. Percentage overshoot, we know the equation. Percentage overshoot, it will be exponential minus pi eta divided by y minus eta squared, multiplied by 100 to be in percentage. Just substitute into this formula and you will get this value. So I guess, yeah, system response was additional pools. If your system is higher order, what will happen? I told you the main form, it should be a second order system, but sometimes you have an additional pool. So we need to investigate the conditions of approximating the behavior of a 3-pole system as that of the 2-pole system, 2 complex dominant poles. I mean, the most important is the 2 complex dominant poles, those are the most important. So this is case 1. So the response will be like this one. If you will add an additional pole, so the response, I mean, this is the second order system. I mean, this one, it is a second order system. If you will add additional pool, maybe the response will be like this one. If this additional pool will be very far away from the G omega axis, maybe the response will be like the second case. So this is case 1. We have case 2. And finally, we have case 3. And in case 3, it is a second order. I mean, case 3, it is a second order system, which we know very well, right? So just adding some additional pools, you should be able to, I mean, know the difference between the 2 responses. Case number 1, the third pool is not much larger than zeta omega n, which is a real part. The third pool is not much larger than zeta. So it's closer to, in fact, when we go back here, this case 1, this is zeta omega n, right? This is delta D, right? So it's not much larger than, so it's so at the distance equal to of delta D from this location, right? Case number 3, the third pool is much larger than this zeta omega n. So it's far away, maybe 6-7 times far away from the G omega plane, maybe 6-7 times. And the case number 3, the third pool is at infinity. You have a third pool, but it's at infinity. When it is at infinity, it will have less impact. It is here located at infinity, right? So it will have, its impact will be much less on the system performance because those are the dominant pools, closed loop pools or conjugate pools. Those are the dominant. So the performance will be specified by this one. But if you have a third pool, which is at a distance of maybe 5-6 times away from the G omega axis, right? Maybe 5-6 times the real part, it will have some impact, but this impact will be much less. You see? So this is the second order system, case number 3. And in this case, we have a third pool at infinity. We have something at infinity. It will not have any impact on your performance because the system will be approximated by the 2 complex dominant poles. The third one will not have any impact. If it's at a distance maybe 5-6 times the real part, what will happen? It will have some impact. So we will have case number 2. It will have some impact. When it is maybe one real part from the complex dominant poles, 2 complex dominant poles, it will have some impact and the response will look like this. So only case 3 can be represented or approximated by pure second order system. Case number 3, if it is at infinity, if the third pool is at infinity, we can just ignore it, right? We can ignore it and we can just represent our system by a pure second order system, right? We just ignore it if it is at infinity. So this is the real part here. If you have a third pool at, for example, S minus 100. So it's very far, in fact, very far. We can assume that it's infinity, right? We can assume that it's an infinity. We can just cancel it. And we can use a pure second order system to represent the behavior of our system. If the third pole is 5 times further to the left, 5 times to the left than the dominant poles, 5 times, the system can be represented only by its two dominant second order pairs of poles. If the distance is more than 5 times, we can just ignore it and we can represent the system by a second order system, right? We just ignore it. If it's at more than 5 times further to the left than the dominant poles, in this case, we can claim that the system can be represented by its two dominant second order pair of poles. Otherwise, we cannot ignore it. If this one is close, less than 5 times, we cannot ignore it and we have to represent it in our system. So we have here, you have a system and we need to determine the validity of a second order approximation. Can we approximate this one using a second order system? Can we approximate this one using a second order system? So we just need to find the real part and calculate the distance between the dominant closed loop system. So we can start with yes, to do this, in fact, to solve it, we need to find the real part, right? So we need to have the pole zero plot. So first we need to, this one, it's 10 times, maybe 10 times 10, it's not possible. We need to solve it, in fact. We need to find the real part. We know the real part here. It's 2 zeta omega n equal 4. So zeta omega n equal 4 divided by 2, which is 2. This is the delta deep. In fact, this is the real part for the system. It's 2. We will see this one, S plus 15. And the 15, in fact, 15 divided by 2, it's around 7.5. So it's more than 5 times away from the dominant poles. So in this case, this system can be approximated as a second order system. So in fact, this one can be approximated as a second order system like this one. This one will be good approximation. It's okay, right? Because this one, it's at minus 15, right? So I mean, my system will look like this one. I have two dominant closed loop poles here. This one, it's minus 2, and I have here one and minus 15. No, this is much far away. It's more than 5 times. Because 5 times it's 10. Minus 2 times 5, like it's 10 plus 2 to minus 12. So it's more than, in fact, to the left. So in this case, we can just ignore this third pole, and we can approximate the system by a second order system or by two dominant closed loop poles. For the system given in P, we will do the same. Here it's because that part is the same, 2 zeta omega n equal 2, so zeta omega n equal 1. So the real part is 1. Correct? So this one will be like this one. But that part will be minus 1, right? This part here will be minus 1. The third one, it's at minus 4. Minus 4. Minus 4, it's 3 times, in fact, or right? Because it's from minus 1, minus 2, minus 3. It's just 3 times away from dominant closed loop poles. 3 times away. When it's less than 5, in this case, we cannot approximate it. And we need to use this one as a third order system. We cannot approximate it as a second order system. So the first one, it can be approximated, but the second one cannot be approximated. Why? The second approximation of this one is valid since the dominant poles have a real part of minus 2. The real part here, it's minus 2. And the higher order pole is at minus 15, which is more than 5 times further, right? So if we need to draw it one more time, it will be like this one. So this one will be at minus 2, and this one it's at minus 15. When it's minus 15, it's more than 5 times further away from the dominant poles, the real part of the dominant poles. For the second system, it's not valid. We cannot approximate it by second order system because the dominant poles have a real part at minus 1. So the second system, we have real part at minus 1 here. And the higher order pole is at minus 4, which is not more than 5 times further. It's just 3 times further, right? 3 times further. This one, how many times further? 2 times 5, it's 15. 2 times 5, it's 10. Yeah, it's more than 5 times. So this one can be approximated, this one cannot be approximated by a second order system. So when you approximate your system, you need to investigate the location of the third pole if it is located 5 times away from the real part of the dominant poles or not. Now we will look into the system response with zeros. This is a system response with no zeros. I mean zeros, it will impact only the maybe gain. Zero looks a simple gain factor and it does not change the relative amplitude of the component of the response. It's just so this is a system with no zero. This one it's at with -10, -5, -3. So in fact, it will impact the gain, and this gain it will impact maybe the maximum overshoot. But the response will be the same, right? So the response has the same shape. So the zeros will just impact the gain, right? And it will impact the maximum overshoot. There is something called the pole zero cancellation. If a zero is at -z, for example, which is very close to the pole at -p3, then they will cancel each other. If you have a zero at -z, which is close to the pole at -p3, then they will cancel each other. Pole zero cancellation, pole zero cancellation. And it's used to approximate or simplify higher order systems. So for example, you have a transfer function, and this transfer function, it's k multiplied by s plus z divided by s plus p3 multiplied by s squared plus this one. If both are close to each other, you can just cancel it with each other. If z is close to p3. So if we need to draw this pole zero plot, this one will give us dominant closed loop poles. It will be like this one. We will get something at minus b3. And also we will get something at z. If minus z. If both are close from each other, in fact, they can cancel each other, and we can simplify the system by the dominant complex conjugate poles. And it is used for, they will cancel each other, right? And we will left with a second order system, which will be much easier to work with. We need to evaluate pole zero cancellation using a residual. There is an approach because we cannot do it. We need to calculate the residuals. In fact, use partial fraction expansion to get the residue of the exponential decay of each pole to see if it is significant or not. So you have this system. We have here, as you can see here, we have here s plus 4. It's a 0 at -4 and a pole at -3.5. Can we cancel this one with this one? So this is problem 1. Problem 2, we have here s plus 4. We have here s plus 4.01. Can we cancel this one with this one? So you need to use partial fraction. If you need to check was this pole zero cancellation is valid or not, you cannot do it by we need to calculate the residual or residue using partial fraction expansion. So for this system, we will use partial fraction expansion. So we will this one will be k1 divided by s plus k2 divided by s plus 3.5 plus k3 divided by s plus 5 plus k4 divided by s plus 6. If we found that k2 is very small, we will just cancel that part because we can assume that it will be cancelled with s plus 4 if k2 is very small, right? So we will do it. So c1 of s will be, it will be 1 divided by s minus 3.5 divided by s plus 5 plus 3.5 divided by s plus 6 minus 1 divided by s plus 5. Residue of the pole at minus 3.5. Yeah, this one, 3.5. Where is, yeah, this one here. This is the one which we need to cancel, for example, because this one can be cancelled with s plus 4. This is the one which we need to test. S plus 3.5 and s plus 4. So we need to check this coefficient. This coefficient residue of this pole, it's equal 1, and it's not negligible. This is large. This number is big number compared to the other residues, right? It's 1, 3.5, 3. So this one is large enough. It's significant, in fact. So in this case, we cannot cancel that part. So just a second order step response approximation cannot be made for C1 of S. We cannot cancel this one with this one, and it says that, okay, my system will be 26.25 divided by that part. No, we cannot do this. Why? Because we checked for the residue of S plus 3.5, and we found that it's significant. It's 1, which is compared to the other residue here, K1, K2, K3, it's still large. So if this one is comparable to those, in this case, we cannot approximate the system as a second order system. So the second order step response approximation cannot be made for C1 of S. We will do it for CT of S. And then when we check it, we found that, you see, this is a term which we want to cancel, S plus 4.01. We need to check if we can cancel this one with this one. So we need to check, we will use partial fraction expansion. And we found that K, this K1, K2, K3, K4 here is very small value compared to this one, and this one. So in this case, the residue of the pool at minus 4.01, which is closest to 0, it's close to 0. When you approximate it, it's close to 0. Close to the 0 at minus 4. I mean, this close to the 0 at minus 4, because here we have S plus 4. This residue is 0.033, which about 2 orders of magnitude below any of the other residues. Hence, we make a second order approximation by neglecting the response generated by the pool at minus. We can just ignore that part. And we can say that, okay, our system approximately will be this one, right? We will ignore that part. And in this case, we will get the time response. So the time response will be minus 4.87 minus 5.3 exponential. If you want to add that part, it will not make any significant change, because it will be 4.033 exponential minus 4.01 t, right? I mean, it's a number will generated from here, but it will be multiplied by this very, very small number. So it will not make any significant change to our final performance. So we can ignore that part. And in this case, we can say that, okay, our system will be approximated to 26.25 divided by S multiplied by S plus 5 multiplied by S plus 6. So even if you want to use those pure zero cancellation, you need to check the residues by using partial fraction expansion. This is very important. We have here skill assessment exercise. Check the validity of the second order step response approximation for each of those. I mean, we need to look into it. You can see here, can we approximate this one as a second order system? Yes, when we look into it, we can see that we have here 0 at S plus 7. We have here a pool at S plus 6.5. So we need to check, can we cancel this one with this one? So the system will be a second order system. So it will be 85.71 divided by S plus 10 multiplied by S plus 20. Can we do this? The same here also, can we cancel this one with this one? So this system will be 197.14 divided by S plus 10 multiplied by S plus 10, 20. Can we do this? We need to do this using partial fraction expansion. So we will do this by partial fraction expansion, and we can find that the coefficient of S plus the pool at minus 6.5, it's 0.3. And in fact, 0.3, it's large compared to 1.5, 0.8, it's significant, right? When it is significant, we cannot ignore that part. So we can say that, okay, this one, it's not possible. We cannot simplify it as a second order system. We will do it also for system B. And when we do it for the system B, we will find that the residue from the pool at S equal minus 6.5, that part, it's equal this small number, 0.07. And of course, 0.07, it's much smaller than 1. It's 10 times less, right? No, it's more. In fact, it's maybe 100 times. Correct? So it's much smaller than this one, much smaller than this one, much smaller than this one. So it's insignificant, in fact. So in fact, we can just simplify this system as 197.14 divided by S plus 10 multiplied by S plus 20. This approximation will be valid, right? It's a good approximation because this 0 will cancel this pool. So the approximation here is valid. So finally, we need to talk about effects of nonlinearities on the time response. I don't want to go into those parts. I want to cancel it. We talk about it already. We talk about it already in chapter 1, and I want to skip it. So 4.10 Laplace transform solution of state equation. I guess we should. Okay, I guess we should finish here, and we will meet again in part 4 of chapter 4. In part 4, we will try to talk about Laplace transform solution of a state equation. So thank you very much.